Cartesian product of sets. So let us understand by using an example. Let
Okay,
set
ma'am.
A is equal to having element A, B, C, and set B we have the elements 1, 2. So let us find A cross B is equal to A, B, C
Okay.
cross 1, 2. And in Cartesian product, we make ordered pair with each element of A with each element of B. Like write down an ordered
Okay,
pair
ma'am.
A, comma 1, A, comma 2. Take next element B, like B, comma 1, B, 2. And now take next element C with 1 and C with 2.
Okay,
So
ma'am.
this is Cartesian product of A and B. Okay.
Okay.
And now let us understand Cartesian product of B and A. Like this, B cross A is equal to, write down first B and then A.
Okay.
Now first we'll take element of B and then along with A. Like 1 comma A, 1 comma B, 1 comma C. Now
Okay,
let us
ma'am.
take 2 with A, 2 B and 2 with C. Now got the
Okay.
meaning of Cartesian product? Got it?
Yes, ma'am.
So this is Cartesian product of two sets. Okay. And if A and B are different, then A cross B not equal to B cross A. They're different.
Okay, ma'am.
You can see here.
Okay.
Okay. Yes. They can only be equal if A and B both are equal, okay, having the same elements. Only then
Okay.
the Cartesian product will be equal. Okay.
Okay. Okay.
Yeah. So now let us understand. You know what function?
Ma'am, could you like revise it a little bit? As in, I do remember it, but I'm not very thorough with it.
Sure, sure. And first of all, let us understand relation, then function, then we'll do group. Okay.
Okay.
Relation. Relation. Let A and B are two non-empty sets.
Okay.
Then relation A to B is a subset of A cross B.
Okay, ma'am.
A cross B. And got this point or not? Because
Yes,
relation
ma'am.
A to B is a subset of A cross B. As
Okay.
we have done this example here, so let us understand this. We have A, example A, B, C, and B is 1, 2, and we have A cross B is
Okay,
equal
ma'am.
to, we have A, 1 and 2. So this is A cross B, and so we can define relation R from
Okay.
A to B, and R is subset of A cross B. Subset means
Okay.
R having any number of elements from this A cross B. Okay.
Okay, ma'am.
If R has few of them, or it can have all, like A comma 1, B comma 2, and C comma 1, having these three ordered pair of Cartesian product, and which are from A cross B, right?
Okay.
So we can say this is relation A to B defined as, or and we
Okay.
can define as A related to 1, B related to 2, A related to 1, B related to 2, and C
Okay.
related to 1. Okay.
Okay.
See, this can have few elements of A cross B, or it can have all of them. Okay,
Okay.
it can have
Yes.
few of them, or because in subset, there are few or all. Okay,
Okay.
elements of the set. Okay,
Okay, ma'am.
so this is meaning of relation. So now let us understand types of relation.
Okay.
Okay. Let A let A be a non-empty set. We are taking only A, and we find a relation in A cross A. A cross A means
Okay.
find its, yeah, non-empty set. Then relation A to A and R is subset of A cross A. Okay, here
Okay,
we
ma'am.
are taking only single set, and we are here define relation as a subset of A cross A. So now let us understand types of relation. First is reflexive.
Okay.
Reflexive relation means relation to itself.
Okay.
Okay. Itself, like if A related to A, B related to B, C related to C, okay, then we can say this is reflexive. Okay,
Okay.
are you getting this point? Because
Yes.
in A cross A, we have such kind of ordered pair in A
Okay.
cross A, as like if you, A we have this. Let us find this Cartesian product by using these elements. So A cross A, we have A comma B, and A comma C. This with all elements. Then now use B with all elements. Then B comma A, B comma B, B comma C. Then C comma A and C comma B and
Okay.
C comma C. Got it? Because this is A cross A. So we'll use means elements
Yes, ma'am.
first from A and second from also A. So we have
Okay.
all possible, yeah, we have this quotation product. So here you can see A, comma A, B, comma B, and C, comma C. So this is reflexive relation. If we have R is equal to like A, comma A, B, comma B, and C, comma C, then we can say that this is reflexive relation.
Okay,
Okay,
ma'am.
got it? Okay.
Yes, ma'am.
Uh, R relation R is A to A is defined as like R is equal to A comma A, B comma B, and C comma C. And we can define these elements as, okay, and we can say this
Okay,
is
ma'am.
relation. This relation is reflexive. Now,
Okay.
next type is symmetric. Symmetric relation. If A related to B, then must be B related to A.
Okay, ma'am.
Then we can say this relation is symmetric, or relation R from A to A is defined as like R is equal to A comma B, B comma
Okay,
A
ma'am.
comma C comma A, or B comma C comma B. Then we can say that this relation is symmetric.
Okay, ma'am.
Here A related to B and B related to A, and B related to C and C related to B, and A related to C and here C related to A. Then then the relation is said to
Okay, ma'am.
be symmetric. Okay.
Okay, ma'am.
Now, next type, transitive relation. If A related to B, B related to C, then
Okay, ma'am.
it must be C related to A, or A related to C. Okay. If any one
Okay,
of
ma'am.
them we have, then we can say the given relation is transitive, or
Okay.
relation R from A to A is defined as R is equal to A comma B, B comma C, and we have A comma C. Or instead of this we have A C comma A, then we can say that the relation is then the relation is transitive.
Okay, ma'am.
And equivalence relation. Next type is equivalence. A relation R is said to be
Okay, ma'am.
equivalence relation if it is reflexive, symmetric, and transitive. Okay, if a relation having all of these three properties, then we can say that the given relation is equivalent.
Okay, ma'am.
Like R from A to A having the subset of A cross A, like A comma A comma B, A comma C, and next B comma A, B comma B, B comma C, C comma A, C comma B, and C comma C. In this A cross A, we have C or symmetric, like having these elements, sorry, reflexive, having these
Okay.
elements, right? And symmetric, having A comma B and B comma A comma C, and C comma A, B comma C, and C comma B. So we have the symmetric relation. Okay, and we have
Okay, ma'am.
like A comma B and B comma C, and also having C comma A or A comma C. So this is transitive also. Okay, so we can say the given relation is an equivalence relation. Okay,
Yes, ma'am.
now let us understand our function. Okay, now let's do function. Give me 1 minute on this.
Okay, ma'am.
Function. Let A and B are two non-empty set. Then function A to B is a rule
Okay.
in which each element of A is associated with unique element of B. Means function is a rule in which each element of the set A is uniquely associated with uh,
Okay, ma'am.
element of B. Okay. So now
Okay.
let us understand by using mapping like a function can be defined as A to B, and this is also we say mapping. Okay,
Okay.
this function is also said to be mapping, and this set is said to be domain, and this is codomain. You know everything, but you need to brush up this, right?
Yes, ma'am.
Yeah. So
Ma'am,
now
because I
let me
studied
say,
all of this 2, 3 years back, and I mean, I studied this in my
yeah.
first year, and after that, I did not
Okay.
study much of math, so that's why.
Okay, okay, I can understand. So let like we have this fx is equal to 2x plus 1. Okay. So now let us define by using this mapping. We have one value of means um, 3 and 4. This is set A and this is B. And if we have this function, now put the 1 here, then we have 3. Now put 2, then we have here 5, 3, 7, 4, and 9. So 1 is associated with 3, 2 with 5, and 3, 7, and 4 with 9. Okay. So
Okay.
each element of B is uniquely is associated with unique element of B. Okay.
Okay.
This is function f. Sometimes we have like this map, this representation, but sometimes they cannot be a function. So let's see in which situation we cannot we say this is not a function. Let us understand this. Okay. Mean this is input. Okay, these elements are input and these are output. Okay, this is input, value of x is input, and this is output we have in set B. And let us understand when they are not a function. Like we have like this, like we have unknown values a, b, c, and d, and x, y, z, and a is associated with x, b is y, and c is also with y, and d is with z. In this
Okay.
situation, we can say this is a function. Why we say this is function? Because more than one element of A can be associated with unique element of B. Why? If we have like a function fx is equal to x square,
Okay.
right? Then if we put like x is equal to 2, then we have fx is equal to 4. If we have x is equal to minus 2, still we have 4, because square of
Okay.
2 and minus 2 is same as 4. So if we have means different input, still we have the same output, right? So in this situation we can say this is a function. Okay, this is
Okay.
a function. This mapping over like a, b, c, d, x, y, z, w, or Like if we have i- if any element of A associated with more than one element of B, then we say this is not a function. Why this is not a function? Because if we put single input, we can't and we never get two outputs.
Okay.
If we put two different inputs, then we can have the same output, right? Here we are using different inputs, still we have same output. But in any condition, we can't get such condition that we put single input, then we'll get two different outputs. So in this
Okay.
mapping, we can say that f is not a function.
Okay. Got it, ma'am.
Okay.
Okay.
Yeah. And let us know in which condition we say this is function or not a function. Let us understand some more by using some more mapping. Like if we have like A, B, C, and D, and U, V, W, X, Y. Like
Okay.
A associated with U, and S with V, W, and X. And here we have Y without associating with any element of A. Right? Then what we say, this is function or not. Let's
Okay.
like in this condition, if we have like fx is equal to like x plus 2. If we don't use here value of any means x, then still we have us any means this 2. Okay.
Okay.
If we don't have any, if we don't use any input, still we have this value. Okay. It
Okay,
means
ma'am.
any element in B can we say without pre-image. Means elements of A are said to be pre-image of elements of B, and elements of B are said to be image of elements of B. So let me define them well. So Y is without any pre-image in A. Okay. So
Okay.
still this is a function because this can be uh, without any value of x. Still we have here by using an example we can understand this. Okay. But
Okay.
so we can say this is a function, and let us understand by using next mapping like A, B, C, and D, and X, Y, Z. Here we have D without image. This is not a function. Why this is not a function? Because when we put any input,
Okay.
okay, then we'll get definitely an output. Okay, this can
Yes, ma'am.
be possible. This can be possible without any value of x, but this cannot be possible when we put any input any. Then we'll definitely get an output. Okay,
Okay.
so any value of A cannot be possible without image of image in B. Okay,
Okay, ma'am.
so let me. So this is not a function.
Okay.
Got this point or not?
Yes, ma'am. I got it.
Okay. So let us understand well image and pre-image. Okay. So let define a function like C B E and U V W X. So A with U, B with X, C with V, D with W, and this with Y. And this is set A, and this is B, and this is function.
Okay.
Does this follow each and every means rule of function? And let us understand image. So image is U and pre-image is A,
Okay.
because A is associated with U. So this says image of A is U and pre-image of U is A. Okay.
Okay.
Now next, element V is associated with X. Okay. So image is X and pre-image is V.
Yes, ma'am.
And next, C with the V, D with W. So and E with Y. So elements of B are said to be image and elements of A are said to be pre-image.
Yes, ma'am.
Pre-image in V and pre-image in set A. So now let us understand now types of function.
Yes, ma'am.
First type, one or injective function. One function or injective function.
Okay.
Just understand first by mapping, then we'll understand by using rule. Set A and set B. When elements of A is each element of A with associate unique element like a single element of A associated with single element of. So this is one. Okay. If we have like this, if you have like this here, two elements of A are associated with single element of B, then we say this is not a one. Okay. So in which condition single element of A associated with single element of B. In this condition, this is 1 function.
Okay.
Got this point or not? Got it?
So, ma'am, technically, every element in A will have only one element in B, right?
Yes. Yes.
Okay.
Yes. Okay. And we also say this is 1 mapping also. Okay. This is 1
Okay.
mapping also. We say this. And now let us understand by using a rule like if because in further means in our syllabus we use this property most frequently if x1 is equal to x2 then it must be fx1 is equal to fx2. It means if we have two equal values then their function must be equal. Okay, then
Okay.
it must be this condition. Okay, and sometime or if functions are equal then it must be x1 is equal to x2. Either they you have to prove like this if you have two equal values then their function must be equal, or sometimes if two functions are equal then you can say x1 is equal to x2. Then we say this function is one function or injective function or injective function. Okay.
Okay.
Shall we do the next or
Yes.
you need to, what do you say?
No, ma'am, we can do one more topic. That's fine.
Okay. Okay. Now let us understand onto function or surjective. If any function is injective and also surjective, then we can say this is bijective. Okay.
Okay.
Yeah. So let us understand surjective by using mapping. A, B, C, D, X, Y, Z, U, V. If we have function like this, A with X, I'm giving you some example to understand in which condition this is on to and which this is not. Here we have this element without pre-image. To
Okay,
be
ma'am.
onto function, it must be that each element of set B must have pre-image in A. So here you can see this element V don't doesn't have any pre-image in set A. So this is not a function, not a onto function. Still this is function, but not onto function. For
Okay.
onto function, every element of B must have pre-image in A. Okay. So we can say this is not onto. In which condition this is onto like A, B, C, D, X. In this condition, this is onto because each element of this set B have the pre-image in A. Okay,
Okay.
means each element of this B is associated with elements of A. So we can say this is onto function. Um, And I'm writing here a function is said to be bijective or onto, sorry, surjective or onto or surjective. If each element of codomain
Yes, ma'am.
must have pre-image in domain. Okay, and uh, F inverse or fx is onto or surjective if f f inverse x exists.
Okay, ma'am.
This is means like rule method, and this is definition. Okay. Next, I'll explain you how to find F inverse in next class.
Okay.
Okay.
Okay, ma'am.
Yeah. And how to find domain and codomain of any given function, and also how to find inverse of this. Okay, we'll do tomorrow. If any function means is injective as well as surjective, then we can say this is bijective function.
Okay, ma'am.
So bijective function is if a function is injective as well as surjective, then it is called bijective.
Okay, ma'am.
Is this enough for today?
Yes, ma'am.
Okay. So let's do now tomorrow.
Thank you, ma'am.
Okay, bye.